Okay, welcome back. How's it going so far? Any good data questions or anything breaking? We were just having to talk about Moore's law before, looking at like what does that look like? Are you in the data exploration phase or the data analysis phase? Which one? Trying to like get stuff done, make some insights, or still trying to figure out what the heck is pandas and why is this zoo animal so important when I'm dealing with Excel files? Graphing. Graphing's good. Explore. Yeah, graphing sort of mix of exploring and sometimes you can actually like make some real insights once you graph it. So if we're in like a graphing kind of phase, and let me load up. So I have like transistor count coming in here. No. Cut those. So if you're trying to grab like a specific column of data, so here if I want that transistor count or date of introduction, you can start typing it. Like if you know at least the first two letters, you can hit tab and it shows you what the options are. So transistor count. And if I want to plot that versus the date, like when was it actually introduced, first just make sure, okay, here we go. At transistor count anywhere from 2,000 to 3 or 30 billion, or wait, 10 to the 9 billion. Yeah, so 30 billion, 22,000 or 2,000. I could try just plotting it, right? Trans of date, again, tab complete. And if I just try like plotting the data, it never hurts to just like try something, right? If I want to know how is this stuff changing, then I get this thing that looks like the world of transistors. Nothing happened until the year 2000 when people slowly started adding transistors to computers, at least on a linear scale, because it was transistors are kind of area based. So if you get one more transistor, you didn't just get one, you got three more. Or at least if you only had one and you added one more in one direction, then you had three overall. And then you had 5 and 5 and like more and more and more. So there's exponential growth. Different ways to kind of look at that. Like I could take the log of the transistor data, and now I have in my head I have to do the math of like, all right, 3 is actually 10 to the 3, 4 is 10 to the 4. Or semi-log y works great. It's a nice like plotting tool that we have. And then I don't have to do math on the data. And then I like markers since I can put it in squares or some squares or circles or even like stars. Like, okay, now I can start seeing all that transistor data kind of laid out rather than looking at a giant table of information. Now it's starting to tell me a story, and maybe I can start telling other people this story about the progress of the microchip and how it all led to you learning pandas in a windowless room here in University of Connecticut. At least it's air conditioning and plugs. We have power. If I'm going to use stars, I want bigger stars. Ta-da! What is it? Opacity? No. Oh, alpha. That's what it is. There we go. I'm just adding like extra stuff to help me visualize it. So if it's really dark, it means a lot of stuff was happening. Really light means not much was going on, just one thing. cells. That one in the bottom. The common thing to do is that you import commands that always at the top. Just basically. Oh, but you want to apply after you define it. Right now, and the reason that I did that is now you can copy that whole cell. You can do one in use build in that first line. Does the drop matter? No. Is it just you're dropping that? No, it's dropping columns of data. So the only thing that matters the most is that now you're not counting the named column, named version. Very last line. Now that one has clean data. Yeah. Yeah, well, at least for me, I'm trying to actually compare stuff. Same axes. Yes, axis. X-Men, yeah. Okay. Okay. That's all right. Yeah. Okay. Nice. I think so. Okay. Yeah, what number can you find for 4 meters? Okay. Yeah, how does percentile work? No, the NP dot percentile. How does that one work? Oh, so you're only using one value. Is that right? Like, what is this output? Like, what is that? That was my question. I couldn't find the fifth edition data. But these numbers, we talked about the same phone. Thank you. I do not know how to use that function, percentile, that you were using. Because like if I look at 0 to 1, oh, that's only one bell. Sorry, I meant to take 11.
Oh, just only one. Well, maybe we can take average before.
Like the 50th percentile, 0 to 1. So uniform is 0 to 1 is 0.5, and 10th percentile is 0.1.
Yeah.
So it's only giving you one output. So it's taking your like the nicely generated random numbers, and then just giving you single value. Yeah, so like if I'm generating random numbers, it's just going to give me that percentile. If I use like normal load equals 0 and scale equals 1. Let's do 10,000. Oh. 50th percentile is going to be basically 0. And then 2.5 it's going to give me like the 2 standard deviation. It's just plugging in the value of 2 standard deviations. So yeah, I guess it works, but
just one.
But you don't really need like random numbers for it. I mean, I guess you can, but really, like this is the same thing as 0 minus 2. -2, -2.
Okay.
Because it's 2 times scale. Is 2.5%. Like, then yeah. it can work, and the bigger this number gets, closer it's going to be to that one. Yeah. Yeah. And if you're like joining online, we're just playing around with like what is this percentile function and trying to figure out like what the outputs are. So it takes a data set and gives you, like if you ask for 2.5, then it gives you the number that is closest to 2.5% of the range of that like sorted data. So when we create it normally distributed, gives us 2 standard deviations versus random. Random. Just give it something big. This one will give us 0.025 because that's the closest number to the 2. That's 2.5% of a uniformly random data. Uniformly random numbers are going to be less than that, and then the other 97.5 are bigger than that number. But yeah, that's one way. One way to like analyze those percentiles. I think quartiles would also be similar. Yeah, how do we find quartiles? Percent. Oh yeah, percentile. Same thing. Yeah. So that could work. Just playing around with different functions, but just the reminder of like how do I use Python? That question mark is like it's your best friend of like how do I use this thing? Just ask Jupyter like what is this thing? Or if you're in an if you're using IPython, same thing. But it shows you all the inputs that you can get, and then shows you everything that it comes out. And then even at the bottom, it shows you different ways of using that function. And usually I skip to the end, figure out like, all right, how is this thing supposed to work? What is it supposed to do? But that question mark is always great troubleshooting. All right, cool. So we're loading up some energy use. Let's. So I had like European use and United States. Like this is total energy. So when I say like total energy use, it's like each year just tallying up how much was used over the course of the year, and then clean slate on January 1st, start adding all that energy up. Some people are like, well, should I add it up so it's a cumulative sum? I'm like, no. It's now we're overthinking it. And you don't have to add up like U.S. plus Europe. It's just two separate things. We just want to compare what did U.S. do versus Europe. They're two similar sized and similar energy sucking entities. Europe has been doing a lot to try to reduce their consumption. U.S. for a while was not, well, kind of was, but then wasn't. Let's put some labels, right? So at some point, something changed. US and Europe both reduced their energy uses by a lot. And then US continued to keep increasing, EU kind of settled out, something changed. But first question is just sort of like, if we squint and say, all right, energy use is a straight line, then what is that line? Like, what's the best line to put through this data? And there's different ways that you can go about that. If you look at like the part 3 kind of reading, it goes into a little more depth into what best fit like how linear regression for straight line approximations works. So linear regression, it has to do with like means and standard deviations. Or, as you can imagine, since we're in Python, we can load in and say US fit is polyfit. Give it the X values, give it the Y values, total or primary. There we go. Primary. I like 2 lines when it starts getting long. So polyfit is a built-in least squares regression function in NumPy. There are other regression fitting tools, but polyfit is the one that's like most used, and it's the most similar to like in Excel. If you say like, give me a line, like give me a best fit line, that's what polyfit would be similar to. Sorry? Trend line, is trend line, does that one give you a function? Is that trend line in Excel? Yeah, so trend line, because sometimes there's also like moving average in Excel. Never use the moving average, it drives me crazy. It just, I've never seen it be helpful because it doesn't even give you an option of like how big the window for your moving average is and what function of moving average. It's just, it drives me crazy. Okay, but we can give it X values, Y values, and then 1 is telling it first order fit, but I can make as big of a fit as I want. And now I could say, once I have that fit, anytime you do a fit, always plot the fit with the data, because otherwise you're reporting like nothing. Like, here's the slope. It's like, well, does it work? Like, does it look like the data? So we always want to look at what happened. US year, and if I have the fit, then I can plot the fit because it's a straight line. One way is this polyval. And I'll probably mess it up, but I think it's US fit and then X values. And if not, then we'll go back in and change it. And we'll do red to match the red stars. Yeah, so it did work correctly. So right now for the US, that's my best fit line. And it's not great, but it's not terrible. Like, well, the world's not linear, man. There's more stuff going on. Like, well, I did things in a polyfit way, so I could make the polynomial as big as I want. How big do we want it? How many terms do you want to fit to a polynomial? 2? Quadratic fit? Does it look quadratic? What do you think? Quadratic, cubic, quartic, pentic? What's fifthic? I don't know. Pentic? Sixic? There's nothing like big, right? It's a 10th order polynomial. Look at that. Beautiful. Maybe the world is a 10th order polynomial and we just didn't know. Maybe bigger. We need more. Bigger is better. This is the US. You want it done right, or you want it done fast? You want it done fast. But it's already warning me, like, hey, your polyfit's not doing so hot. It's like, quiet you, 15. And it just keeps getting better. Everything's better. Life is good. This just looking great. Everything's great. So why don't we just use like higher and higher order polynomials? It surpasses it? How big is our data frame? That's my first question. 54. Okay, so technically we should be able to fit a 53. We should be able to fit 53 order, right? If we have 54 data points, then there are 54 constants that we could solve for. One of them is year to the 0. And it's warning, it's giving me warnings, but it's showing me gold. All right, let's do this. I'm going to define my own time. So I have a function. I can define any point in time because I did a best fit function. And look at, what did I do wrong? Time and time. Oh, whoops. I messed it up. There we go. All right, how does my prediction look now? I extended it 5 years into the future. Super accurate. Excellent work. Close the books. This is usually the main problem, is like the higher order polynomials, the more wiggly they get, so the more unpredictable they get. Because if I change this from a 53 to a 52, it still goes up. Sometimes it flips. It'll be like, there's going to be a huge decrease, like everything's going down, but in this case it didn't happen to. So rule of thumb, usually people stick to 3 as like a, order 3 is like high enough. Unless you physically know something about like what's going on, like there is a reason to fit higher order polynomials or something. But anyway, yeah, the only thing that you're asked to do is do first order fit. And we even extend it out to 2025. Get a prediction out there. Ooh, bless you. All right, thanks for the work. Keep it up. And then we'll come back on Friday, right? Friday? Today's Wednesday.